Welcome to the Deep Dive, where we take your stack of sources, find the essential connections, and hand you the synthesized knowledge you need to be thoroughly and surprisingly well-informed.
Today, we are undertaking a pretty monumental task. We are not just running down a chronology of technological inventions.
No, not at
Our
all.
mission is to trace the 5,000-year story of humanity's singular, relentless effort to externalize its own complex mental processes.
So we're talking about calculation, but also the symbolic manipulation of reality itself.
Exactly. We are charting the evolution of computing as an act of externalized human cognition.
I love that frame, cognitive externalization, because the history of computing suddenly stops being about, transistors and gadgets.
Right.
It starts being about how we automate human thought. We're charting this journey from ancient counting aids through 5 distinct hardware generations, all the way to the pervasive invisible distributed architecture of the modern cloud.
Precisely. The goal here is synthesis. We need to identify the key breakthroughs that made computing powerful, then made it affordable, and finally, what made it globally accessible.
Okay, let's unpack this grand vision. Our sources today are dense and pretty rewarding. They cover everything from the necessity of ancient trade regulation to the competitive, war-driven birth of electronics.
And the rise of the backyard hobbyist?
Yes, and all the way to the very specific, detailed definitions that govern contemporary network architecture today.
So you are about to get a shortcut to 5,000 years of revolutionary thought.
So if the story starts in antiquity, we're talking before silicon, before we even had electricity, it really starts with a deep, fundamental societal necessity, right?
Oh, absolutely.
You can't have a complex civilization without complex accounting.
Exactly. Calculation wasn't some, academic exercise. It was integral to how early societies functioned. The Egyptians, the Greeks, and especially Mesopotamians relied on it
For what, specifically?
to regulate complex trade economies, to manage these massive building projects they were undertaking, and to fix the dimensions of land for things like taxation and farming. This necessity drove the immediate need for reliable, externalized memory aids.
And those earliest devices were incredibly simple, what you might call physical bookkeeping.
Indeed. The primitive system started with just simple physical aids. We're talking about things like counting sticks or using specific knots in a piece of rope.
Tally sticks too, right? With the notches.
And tally sticks, which use deliberate notches to denote values. These systems and some early forms of writing that use shorthand to represent large quantities were really the first steps toward abstracting numbers from the things they actually represented.
But the real leap, the transition from just simple record keeping to actual manipulation and, calculation, that seems to be the abacus.
Yes.
That was the first device that consistently translated mathematical logic into a physical, repeatable state.
That's the absolutely crucial distinction. The abacus, which evolved in various forms across Eurasia between about 2700 BCE and 500 BCE, it moved beyond being just a memory aid. Our sources highlight that it incorporated 4 central components that essentially define a computational structure.
And these set the stage for everything that followed.
Everything.
So what are those 4 components?
Okay, so first, you have the representational medium, in this case, the rods and the beads. Second, you have the defined relationships between those components that represent specific numbers, like place value.
Okay, makes sense.
Third are the transformation rules, which is just moving the beads to mirror mathematical operations like addition or subtraction. And fourth, you have the control structure, which in this case was the human operator following those rules.
And that operator was working with incredible sophistication, depending on the version. You pointed out the Chinese swanpan as a particularly complex example.
It is a remarkable piece of engineering, even though it's purely manual. The swanpan used an upper deck of 2 heaven beads, and each of those was valued at 5.
And the lower deck.
A lower deck of 5 earth beads, each valued at 1. This design wasn't just limited to base 10, it was systematic enough to efficiently support both decimal and duodecimal calculations.
Base 12.
Base 12, which was common in trade systems involving time or measures that divide easily by 2, 3, 4, and 6.
That structural ability to physically model different mathematical systems must be the key takeaway here.
It is the profound theoretical significance. This systematic, physical manipulation of beads established a state that perfectly mirrored mathematical logic.
So it's a physical analog for a logical process.
Precisely. And because the abacus can perform any sequence of basic arithmetic operations, it is the earliest known device to which the concept of Turing computable functions are theoretically applicable.
Wow.
It laid the conceptual groundwork for the idea that computation, no matter how complex the problem is, can be reduced to a finite set of systematic mechanical steps.
And that idea, dating back 4,000 years, still underlies all modern computer science.
It's the foundation of everything.
Okay, so the abacus proved we could externalize arithmetic. But the next major jump wasn't just about calculation. It was about automating the manipulation, right? Reducing the physical human effort.
Yes, and this takes us into the 17th century. It was driven by new theoretical math and an almost aesthetic fascination with gears and stockwork.
That early modern period's fixation on clockwork and automation combined with theoretical advances, that was the catalyst.
It really was. People were designing automatons and these intricate timepieces.
Yeah.
The idea of a machine that could think or, calculate was a natural extension of that whole engineering drive.
And before we got the machines, there was a necessary mathematical breakthrough. We're talking about John Napier's work.
Napier was truly revolutionary. In 1614, his discovery of logarithms provided the theoretical backbone for the slide rule.
A tool that was essential for engineers and scientists right up until the late 20th century.
Absolutely. Logarithmic scales essentially allow you to turn the more difficult operations of multiplication and division into the simpler operations of just adding and subtracting segments.
Can you walk us through that specific mechanical advantage? How does that work in practice?
Sure. Think about it this way. To multiply two numbers, say 2 and 3, on a slide rule, you physically take the length representing the logarithm of 2, and you physically add it to the length representing the logarithm of 3.
Okay.
The total length you get corresponds to the logarithm of the product, which is 6. You've just replaced complex multiplication with simple physical movement.
It's an elegant mechanical trick that radically sped up large-scale calculations.
It really is.
So the slide rule is the practical application of logarithms, but Napier also gave us the hardware template for automation itself, with his bones.
Yes, Napier's bones, which he devised in 1617. They were sets of rods used for multiplication via repeated addition and subtraction. Now, while they were manual, a boxed version of these rods provided the conceptual template for one of the most significant mechanical challenges in calculation.
And that was the gear-based carry mechanism.
That was it. That small feature, the way a machine shifts from 9 to 10 and propagates that change across multiple digits, that was the missing piece for automated calculation.
Which leads us directly to the first serious attempts at true mechanical calculators.
Starting with Blaise Pascal's Pascaline in 1642, Pascal developed it to assist his father, who was a tax collector, and was managing these massive ledgers full of sums.
And the core innovation was that gear-based carry mechanism for addition and subtraction.
It was, but the sources highlight a major engineering hurdle he faced that really limited the Pascaline's use.
A profound hardware limitation.
Exactly. When a carry had to be propagated across multiple digits, for example, if you're calculating 99,999 plus 1, the force required to trip all the gears in a cascade could cause the entire delicate mechanism to jam.
So the hardware itself was fighting the speed of the math.
It was. This limitation meant the Pascaline was largely impractical for widespread use, even though it was conceptually a masterpiece.
So who was the next person to tackle this problem?
That would be Gottfried Wilhelm von Leibniz. He took up the challenge with the stepped reckoner in 1673.
And he managed to improve on Pascal's work.
Significantly, he incorporated a specialized cylindrical drum mechanism known as the Leibniz wheel that could perform all 4 basic arithmetic operations automatically: addition, subtraction, multiplication, and division. This was a true 4-function machine.
Leibniz seems to have been both a great engineer and a great visionary.
Oh, absolutely. Beyond just the hardware, Leibniz was a key advocate for binary arithmetic. He correctly envisioned that a system based only on ones and zeros on-off, true-false, was the most efficient way to mechanize logic and calculation.
An insight from the 17th century.
From the 17th century, and it's the bedrock of all digital computing.
The ultimate goal of all these mechanical devices was the pursuit of, well, superior error-free calculation. And this brings us to Charles Babbage, who essentially attempted to build a digital computer using 19th century steam power and brass.
The motivation for his difference engine, and later the analytical engine, was purely practical, eliminating human error. Complex tables of logarithms, navigation data, trigonometric values, they were all calculated by these error-prone human computers.
Babbage sought mechanical perfection.
He did.
It wasn't entirely his unique idea, though. It started with the concept of a difference engine.
That's right. A man named Johann Helfrich von Müller conceived of the idea back in 1786. He specifically envisioned a machine that would calculate and print logarithm tables perfectly.
But Babbage, 40 years later, designed a far more complex machine.
Much more complex. It was intended not only to calculate, but also to automatically stereoprint the tables, which would eliminate the last possible point of human error, setting the type.
So why did Babbage's ambition ultimately fail during his lifetime? Was the concept flawed?
The concept was perfectly sound, and we know that because of the fragment that was reconstructed by his son Henry later on. Babbage's failure was purely a function of the technology of his day.
The manufacturing wasn't there yet.
Exactly. His design required mechanical components, gears, levers, linkages, to be manufactured with an incredible precision that 19th century machine tools just could not achieve consistently. The tiny deviations in the brass and iron parts introduced cumulative errors, rendering the machine unreliable at scale.
So the conceptual hardware design was literally ahead of the material science needed to build it. That must have been incredibly frustrating.
Terribly so. And this led him to his magnum opus, the analytical engine, which was the first design for a general-purpose programmable computer.
It included elements we'd recognize today, right?
Absolutely. It had the mill, which was basically the arithmetic logic unit where calculations happen, and the store, which was the memory or data register. He even envisioned using punched cards, adapted from the Jacquard loom, for inputting both instructions and data.
That sounds like a modern CPU and RAM governed by programming.
Precisely. Babbage, along with Ada Lovelace, who really understood the potential of the machine to manipulate symbols beyond just numbers, truly laid the conceptual groundwork. The designs of these mechanical masters, using all these geared mechanisms to store information in registers, established the intellectual architecture of memory storage and instruction execution that we still follow today.
That mechanical era, while it was conceptually rich, was fundamentally constrained by the speed and reliability of moving parts.
It was.
The true accelerant for computing wasn't academic curiosity or tax efficiency. It was the existential threat of global conflict. The mid-20th century saw this massive leap to electronic pulses, driven by the need to accelerate ballistics calculations and cryptanalysis.
The leap required was revolutionary. It meant replacing slow, heavy mechanical switches and all those moving parts with electronic components. This marked the start of the first generation, from about 1948 to 1956.
And it was characterized by the use of massive vacuum tubes for circuitry and memory.
Yes, which were essentially just electronic switches.
And the cost of this shift was immediate and staggering.
Oh, yes. It resulted in machines of enormous size, astronomical complexity, and just massive power consumption. For context, ENIAC required 150 kilowatts of power.
Enough for a small town.
Enough for a small town. And it generated an intense amount of heat, which was itself a major maintenance problem.
And crucially, the innovation here was happening in parallel, often in isolation and under deep wartime secrecy. Let's start with Konrad Zuse in Germany, working basically on his own.
Zuse is a fantastic example of a brilliant mind working outside the major institutional framework. His Z3, which he completed in 1941, was the world's first fully functional, program-controlled electromechanical digital computer.
So not fully electronic.
Not fully electronic. It relied on 2,300 high-speed electromagnetic relays, not vacuum tubes.
And what was its primary function?
It was used for aerodynamic calculations for the German military. But Zuse's lasting contribution was demonstrating unequivocally that binary logic, the language of ones and zeros, was the most efficient, logical, and compact way to mechanize calculation. He built it using the simplest form of internal logic possible.
Okay, so across the channel, the British were building their own secret weapon, which was faster because it was fully electronic.
That was the Colossus, designed by Tommy Flowers and operating at Bletchley Park. It was the world's first programmable electronic digital computer.
And it was built specifically for cryptanalysis.
Exactly. It was tasked with cracking the complex, multi-layered Lorenz ciphers used by the Nazi high command.
The speed must have been incredible, achieved purely through electronics.
Colossus achieved its speed by using up to 2,500 vacuum tubes for high-speed Boolean logic and counting. It was a massive machine, built to perform rapid pattern matching.
And its existence was kept secret for decades.
One of the deepest state secrets of the war, right up until the 1970s. Many historians credit its ability to process intercepts so quickly with actually shortening the European war effort.
And finally, the American effort, ENIAC, the Electronic Numerical Integrator in Computer.
ENIAC was the grandest effort yet. It was completed in 1945 by John Mauchly and J. Presper Eckert for the U.S. Army's Ballistic Research Laboratory.
The physicality alone is staggering.
It is. It weighed 30 short tons, occupied 300 square feet of floor space, and contained 18,000 vacuum tubes and 5 million hand-soldered joints.
And what was the performance leap? How much faster was it?
It was revolutionary. ENIAC was over 1,000 times faster than any previous electromechanical machine. It was capable of processing about 500 floating-point operations per second, or FLOPS.
Which sounds tiny now.
It is. Today's average smartphone operates in the teraflops range, trillions of operations per second. But in 1945, 500 FLOPS was a performance barrier that was broken by orders of magnitude.
And the sources note its very first task was not the ballistics it was designed for.
No, it wasn't. Its initial program was a critical study of the feasibility of the thermonuclear weapon, the H-bomb. It's often said that ENIAC performed more calculation in its first few years of operation than all of humanity had performed up until that time.
It truly marked the point where computation became a force multiplier in science and defense.
A completely new era.
And here is where we can connect back to that theme of cognitive externalization, because the human effort required to make these monsters work was immense, and it was driven by an often overlooked group of pioneers.
Absolutely. The complex task of programming ENIAC was originally handled by 6 female mathematicians: Kay McNulty, Marlon Westcott, Ruth Lichterman, Betty Snyder, Frances Bylas, and Jean Jennings.
And they were hired as human computers during the war.
That's right.
But they weren't just inputting data, they were the software engineers, physically wiring the machine.
That's the critical insight. Programming ENIAC involved physically mapping the problem's logic onto the machine itself. They had to use plugboard wiring, physically connecting cables, and then manipulating 1,200 switches on these portable function tables to define the sequences of operations.
That's a monumental, painstaking cognitive task.
It is. Conceptualizing the math, breaking it down into machine steps, and then translating those steps into physical connections.
So they were creating the software by modifying the hardware, in a sense.
Precisely. For example, Snyder and Jennings were responsible for creating the missile trajectory demo for the 1946 press unveiling, and that required weeks of preparation. Their expertise was so deep that when the massive machine invariably broke down,
Which it did all the time.
As vacuum tubes regularly failed, they were often able to locate bugs down to the individual failed tube through sheer logical deduction and pattern recognition. They were the original debugging pioneers.
But their work immediately highlighted the major inefficiency, the programming bottleneck of the entire first generation.
Yes. ENIAC's fixed program required weeks of design and days of physical rewiring for every single new problem. So if the machine could execute a calculation in seconds, but it took days to set up, the throughput was terribly limited.
And that massive inefficiency spurred the development of the most foundational conceptual shift in modern computing.
The stored program concept.
Right. Eckert and Mauchly conceived of the idea of storing instructions in the same electronic memory as the data during ENIAC's development. But it was John von Neumann who really formalized it.
Von Neumann synthesized these revolutionary ideas in his pivotal 1945 paper, the first draft of a report on the EDVC. This report outlined the architecture, where instructions and data share a common addressable memory.
A structure that forms the basis of nearly all modern central processing units and is known today as the von Neumann architecture.
That's the one.
And the British, building on that wartime electronic leap, were the first to implement this idea practically.
Indeed. The Manchester Baby in 1948 was the first fully electronic computer to successfully run a stored program. And then the EDSC, completed at Cambridge in 1949, was the first practical stored program computer to provide a regular service to the scientific community.
And it used Maurice Wilkes's innovation of subroutines.
Which was the birth of modular reusable code stored on punched paper tapes for common repetitive calculations.
But the stored program concept itself, while it solved the programming bottleneck, it introduced a new, famous limitation, one that still governs system design today: the von Neumann bottleneck.
This is a crucial takeaway. It's the intellectual legacy of that architecture. Because the von Neumann architecture uses a single shared communication path, single bus, for both instructions and data traffic between the CPU and memory, throughput is severely limited compared to the blistering speed at which the CPU can execute instructions.
So the processor's waiting on the data, and the instructions are waiting on the data, and they're all fighting for the same narrow highway.
That's a perfect analogy. You have a Formula One race car, the CPU, waiting to get its fuel, the data, and its route instructions, the program, through a single toll booth, the bus. Even if the car is infinitely fast, its performance is constrained by that single fixed-width road.
And the late John Backus in 1977, he elevated this from a technical problem to an intellectual one.
He argued that this architecture was not only a literal bottleneck for the data traffic, but also an intellectual bottleneck that promoted word-at-a-time thinking.
What did he mean by that?
Backus suggested that programmers, constrained by the architecture, were forced to focus on the mechanical shuffling of data back and forth, rather than focusing on the high-level logic of the problem itself.
So the bottleneck isn't just about speed, it's about how we think about writing programs.
Exactly. Modern systems, of course, they mitigate this issue. They use separate caches for instructions and data, creating a modified Harvard architecture, and they employ complex branch prediction algorithms to anticipate data needs.
But the core limitation remains.
The intellectual focus on memory management, it remains an important point of discussion in advanced systems architecture, even as we move toward highly parallel processing.
Okay, so the history of computing then becomes a history of just shrinking components. Moving from ENIAC's 18,000 glowing vacuum tubes to solid-state electronics changed everything. It made computers reliable enough for the commercial world.
That's the solid-state leap, covering generations 2 and 3. The second generation, from about 56 to 63, kicked off with the invention of the transistor at Bell Labs in 1947.
And these tiny solid-state switches made machines smaller, faster.
And most critically, orders of magnitude more reliable because they generated almost no heat compared to the tubes.
Reliability must have been the biggest business driver.
Oh, absolutely. The massive failure rate of vacuum tubes made that first generation cost prohibitive for business. Transistors made computers viable for commercial and research applications, leading to machines like the highly successful IBM 7090.
And the third generation was the next logical step, cramming more and more components onto one tiny surface.
The third generation, 64 to 71, saw the debut of integrated circuits, or ICs. This is where engineers etched multiple transistors, resistors, and capacitors onto a single silicon chip.
And this drove extreme miniaturization and manufacturing efficiency.
It did. It enabled machines like the IBM System 360, which demonstrated the versatility of ICs across a huge range of business and scientific fields.
And it was during this generation that computers first started escaping the massive air-conditioned data centers.
Yes, the first step toward democratization came via the minicomputer. The Digital Equipment Corporation's PDP-8, for instance, was released in 1965, and it sold for $18,000.
Which sounds expensive now.
But it was one-fifth the price of a small IBM mainframe. This dramatic cost and size reduction made it commercially successful, marking the initial crucial shift toward widespread accessibility for plants, small businesses, and scientific labs. They no longer needed to share time on massive mainframes.
The true inflection point in history, though, the moment computing went from being institutional to personal, came with the fourth generation, the microprocessor. It is truly hard to overstate the importance of putting the entire central processing unit onto a single chip.
That single chip meant the size and cost of the core thinking mechanism of the computer just plummeted, and that enabled the revolution. The first commercially available microprocessor was the Intel 4004 in 1971.
And it was designed for a calculator company.
A Japanese calculator company, yes. This foundational technology is what made personal computers feasible.
And that technological leap led directly to the explosion of the hobbyist and hacker culture, embodied by the Altair 8800.
The Altair 8800, based on the Intel 8080, appeared as a kit on the cover of Popular Electronics in January 1975.
And it sparked thousands of unexpected orders from hobbyists.
It did. It was incredibly primitive. You programmed it via these tiny toggle switches, and the output was just shown on flashing LEDs, but it inspired the phrase personal computer. It established the early computer clubs and that whole spirit of tinkering.
And it famously inspired two young innovators.
Indeed. It inspired Bill Gates and Paul Allen to write the first basic programming language interpreter for the machine. That gave the Altair its first real software language, and it set them on the path to creating Microsoft.
The Altair was the spark that created the market. But the IBM PC was the machine that legitimized it and standardized it for the entire corporate world.
Right. When IBM released the IBM PC in 1981, their strategic decision was key. They chose an open architecture, they used off-the-shelf components, notably the Intel 8088 CPU, and they licensed the operating system, MS-DOS, from Microsoft.
This was a radical departure from the closed, proprietary systems of the era.
It was.
So the key wasn't better technology, but the strategic decision to make the platform open.
Precisely. That move, backed by IBM's corporate legitimacy, instantly established the dominant industry platform. More importantly, it spurred a vibrant, competitive third-party software and hardware ecosystem, the clone market,
Which rapidly innovated and slashed costs.
and made the PC the undisputed standard tool for office and personal work globally. That open standard drove affordability and scale.
And then came the revolution in user-friendliness, the graphical user interface.
That credit goes to a specific lineage of cognitive externalization. The idea of using a mouse and icons was originally pioneered on the expensive Xerox Alto in 1973.
But it was Apple that brought it to the masses.
Yes, it was Apple's Lisa in 1983 and then the Macintosh in 1984 that brought the intuitive graphical interface to the mass consumer market. They made computing accessible for the non-technical user. You no longer had to memorize command line instructions.
And if we look back at the sheer scale of adoption, the sales champion for the fourth generation is still the Commodore 64.
Released in 1982, it sold over 22 million units worldwide. It's in the Guinness Book of World Records for that.
That huge commercial success really highlights that the shift was complete.
It was. From computing as a specialized science to computing as a consumer product, a tool for education, gaming, and basic productivity.
As we move closer to the present, the miniaturization never stopped. It even reached the point of smart dust. This takes Babbage's desire for precision to an entirely new level.
The pursuit of ever smaller size reached its functional limit with things like the University of Michigan Micromote, completed in 2014. It measures just over 1 cubic millimeter.
They're known as smart dust.
That's right.
What are they used for, given their size?
Well, they're powered by tiny photocells. They consume only about 1/1,000,000th of a watt, and they're designed for sensors, measuring things like temperature, pressure, and images in highly distributed, hard-to-reach environments.
Like inside the human body or deep in industrial machinery?
Exactly. They represent the ultimate endpoint of miniaturization, a computer that is almost invisible.
But at the same time, this era also saw the democratization of hardware design itself, moving back to the spirit of the Altair hobbyists, but with modern components.
That's where we see the rise of low-cost, credit card-sized single-board computers like the Raspberry Pi in 2012 and microcontrollers like the Arduino in 2005.
And these devices have democratized computing for education and the global maker movement.
They empower anyone to build customized, tangible applications and physical computing projects, proving that the desire to build and control the hardware remains strong even as the rest of the world moves toward abstraction.
So we've tracked computing from a bead to a gear to a room full of tubes to a single chip. But the final major leap wasn't about shrinking the hardware. It was about abstracting the machine entirely, starting with connectivity.
The moment the individual computer was linked to others, its utility was exponentially multiplied. And the philosophical foundation for treating computing as a shared, abstracted resource was laid very early.
How early?
Back in 1961, Professor John McCarthy envisioned computing packaged as a public utility where subscribers would pay only for the capacity they actually use. That is, conceptually, the cloud.
The first concrete step toward that utility model was, of course, ARPANET.
Launched in 1969, ARPANET was created for decentralized resource sharing among research institutions, and its architectural brilliance lay in the non-fragile concept of packet switching.
How was that different from the old way of communicating? The phone network.
Right. Traditional telephone networks use circuit switching. When you made a call, a dedicated physical circuit, a single path, was reserved between you and the other party for the entire duration of the call. If that circuit broke, the call dropped.
Simple as that.
Packet switching, conversely, breaks data into small, self-contained packets that can dynamically navigate through any available path to the destination. If one path fails, the packets simply reroute instantaneously.
That sounds like a much more resilient, scalable system.
It is the definition of resilience. The network itself became the infrastructure, not the physical wires connecting two specific points. But for these diverse networks to truly talk to each other, they needed a common language.
And that was TCP/IP?
Vint Cerf and Bob Kahn's contribution in 1973, the Transmission Control Protocol Internet Protocol.
What did each part do?
So TCP manages the reliable delivery of packets, ensuring all the little pieces arrive and are reassembled correctly. IP manages the addressing and routing. This protocol allowed diverse networks running different operating systems, different hardware, to communicate seamlessly.
And when ARPANET adopted this standard in 1983, that's when the modern internet was essentially born.
That was the moment.
The internet gave us the wires and the common language, but the World Wide Web gave us the human-friendly interface, the global window we all recognize.
And that was Tim Berners-Lee at CERN in 1989. He brilliantly merged the existing network infrastructure with the concept of hypertext nonlinear information linking by creating the standards for URLs, HTTP, and HTML.
And the Mosaic web browser in '93 was really the key moment.
It was. It transformed the complex text-based computer interface into a user-friendly graphical information tool, and that sparked the massive explosion of adoption we saw in the mid-90s.
Now we arrive at the final abstraction, cloud computing. The term itself is great. It implies that the machine is just an amorphous cloud of capability, hiding the actual servers from the user.
The ISO definition is key here. It defines cloud computing as a paradigm that enables network access to a scalable and elastic pool of shareable physical or virtual resources with self-service provisioning and administration on demand.
It's the logical successor to utility computing and grid computing.
Exactly.
What are the defining characteristics of this new paradigm? The sources give us the 5 essential traits defined by NIST, the gold standard definition. Let's go beyond just listing them and explain what they mean operationally.
Okay, these 5 characteristics define the economic and operational model that makes the cloud so revolutionary. First is on-demand self-service.
Meaning you don't have to call anyone to get a server.
Right. A consumer can provision computing capabilities like server time or storage automatically without needing to talk to a human service provider. You click a button and the resource appears.
Okay, number 2.
Broad network access. The capabilities must be available over the network via standard mechanisms. This promotes use by heterogeneous platforms, your phone, your tablet, your laptop. The cloud has to be accessible from any device.
Third is resource pooling.
Right. The provider's computing resources are pooled, physically managed in huge data centers to serve multiple consumers using a multi-tenant model. Resources are dynamically assigned and reassigned according to demand. You don't know which physical server your data is on, you just know it's available.
And number 4 is probably the most famous one, rapid elasticity.
This is the core appeal and the key to its economic efficiency. Capabilities can be elastically provisioned and released, scaling rapidly outward and inward commensurate with demand.
That rapid elasticity must be what convinced every business to migrate.
Oh, absolutely. To the consumer, the available capacity often appears unlimited. If your website suddenly gets 10 times the traffic, the cloud scales up capacity instantly and automatically and then scales it back down when the surge passes.
So you're never over-provisioned during quiet times, and never overwhelmed during peak times.
Precisely. And the 5th is measured service. Cloud systems automatically control and optimize resource use by leveraging a metering capability. This provides transparent tracking for both the provider and consumer on resource usage.
You pay for what you use.
Down to the second or the byte.
That measured service is what sold the model. But the commercial birth of the cloud, as we know it today, was actually driven by an unexpected internal architectural problem at Amazon.
That is truly the genesis story of the infrastructure as a service model. Amazon's initial web presence was built on this limiting monolithic architecture, a single, massive, interdependent code base trying to manage everything.
Which caused frequent internal conflicts and downtime.
It did. So to scale their retail side, they had to break the monolith.
They had to internally separate their entire architecture into smaller, independent microservices.
Units that could communicate with each other but operate and fail independently. This internal innovation, combined with extensive virtualization technology, allowed Amazon Web Services, AWS, to launch Simple Storage Service, S3, and Elastic Compute Cloud, EC2, in 2006.
Pioneering the IS model.
They pioneered the infrastructure as a service model pay-as-you-go processing and storage. They realized the massive, efficient, resilient infrastructure they had built for themselves could be sold as a utility to everyone else.
The cloud isn't a single product, though. It's a stack of services, giving users varying levels of control and abstraction. So how do we break down those service models that sit on top of the physical infrastructure?
The service models are universally arranged like a technology stack, IFS, PaaS, and SaaS. And each one represents an increasing level of abstraction where the user controls less of the underlying physical architecture.
Let's start with IS.
So IS, infrastructure as a service, is the foundation, pioneered by AWS EC2. The consumer controls the deployed applications, the operating systems, the storage and networking components. but you do not manage the underlying physical infrastructure.
You control the software layer, they control the hardware layer.
Exactly. Next up is PaaS, Platform as a Service. Here, the abstraction increases. The consumer deploys their applications and manages the code, but they give up control of the underlying infrastructure, the OS, server software, networking to the provider. It's a managed, ready-to-use environment for building and running code.
And the highest level is SaaS.
SaaS, Software as a Service. Here, the consumer simply uses the provider's application via a thin client, usually a web browser. You only control limited user-specific configuration settings. Think of Microsoft 365 or Salesforce.
And the ultimate abstraction of this trend is serverless computing, where the user moves beyond the stack entirely.
Serverless is exactly that. The user provides only their application code, often in small executable functions, and the cloud provider manages all underlying hardware provisioning, deployment, and scaling automatically.
And they charge you only for the milliseconds your function actually runs.
Right. The user stops worrying about servers, operating systems, or capacity planning entirely. They only care about their application's function.
Architecturally, though, most large organizations don't stick to one model. The sources highlight the different deployment models they use to manage their resources across various locations.
We define three primary deployment architectures. First is the public cloud, delivered over the public internet. This is dominated by the hyperscalers AWS, Microsoft Azure, and Google Cloud.
Okay, second.
Private cloud, operated solely for a single organization, whether it's managed internally or by a third party. This offers maximum control and security, but is often capital-intensive and has significant overhead.
As the critics say, with a private cloud, you still have to buy, build, and manage the infrastructure yourself.
That's the argument. And third is the hybrid cloud, which is the most common reality for large enterprises. It's a composition of public and private environments that remain distinct, but are bound together by standardized technology.
This allows organizations to balance their needs.
Exactly. They can maintain control over sensitive, regulated data on premises while leveraging the vast scalability and cost-effectiveness of the public cloud for burst capacity or less sensitive data.
With all this power, elasticity, and abstraction, what are the modern challenges users face? Because moving to the cloud isn't a silver bullet. The problems shift from hardware failure to governance.
The challenges fundamentally shift from managing physical hardware to managing costs and security governance. Regarding costs, users often face unexpected complexity and massive bills due to inefficiency.
Like what?
Things like hidden costs, leaving virtual machines running unnecessarily, or just failing to efficiently configure provisioned resources.
Which has led to the rise of specialized disciplines.
Yes, the complexity of measured service, that fifth NIST characteristic, has led to the rise of FinOps, or cloud financial operations. FinOps is an organizational discipline that brings financial accountability to the variable spend model of the cloud.
So it's about making sure you're not wasting money.
It's about practices and tools that help organizations manage, optimize, and forecast their cloud costs effectively to maximize the economic value of their public cloud usage.
And security changes fundamentally when your data lives on someone else's infrastructure, which brings us to the shared responsibility model.
This model is critical for any cloud user to understand. You're entrusting sensitive data to third-party providers, which introduces security and compliance risks, like with GDPR or iPay. The crucial point is the strict division of labor.
How does that division work?
The cloud provider, like AWS or Azure, is responsible for the security of the cloud. They handle the physical security of the data centers, the underlying hardware, the global network, and updating the base software.
But the customer.
The customer is responsible for the security in the cloud. This includes customer data encryption, identity and access management, firewall configurations, and application-level security.
So if your data is breached because an employee had a weak password,
that is the customer's responsibility, not the provider's. And this balance of responsibility shifts depending on the service model. IaaS gives the customer way more responsibility than SaaS. Hashtag outro.
It is incredible to reflect on this entire journey. We started with ancient humans trying to externalize memory and regulate trade with notches on a stick. We moved through centuries of fragile gears trying to perform calculation, and then through massive, hot, wartime electronics.
And now
we are managing global, abstract, distributed systems where the physical machine is essentially irrelevant to the user.
the core driver remains absolutely constant. The relentless pursuit of error-free efficiency and seemingly limitless on-demand capacity. We observe the transition from monolithic, expensive institutional computers like the ENIC.
To the mass democratization of the integrated circuit and the personal computer.
And finally, we arrived at the complete abstraction of the architecture itself in the cloud.
The focus of complexity has moved. The initial goal of the ENIAC was to externalize the process of calculating the trajectory of an artillery shell in a matter of seconds.
And the challenge today is no longer about one complex calculation. It's about managing real-time, global, elastic resource pools serving billions of concurrent users and applications.
Allocating that infinite capacity efficiently and securely.
That immense scale of resource allocation is the modern engineering problem.
So we circle back to the concept of cognitive externalization. We've built an infrastructure that gives us virtually unlimited elastic brain capacity on demand. We talked earlier about the von Neumann bottleneck, the architectural limitation that John Abacus described in 1977 as an intellectual bottleneck.
Yes, that focus on mechanical data movement rather than high-level problem solving.
So if the history of computing is about externalizing our brain power, and cloud systems offer this seemingly unlimited elastic capacity, does that original intellectual bottleneck still persist? And if we rely entirely on this managed, potentially limitless resource pool, how does that fundamentally change how we frame and conceive of problems and knowledge itself?
Does it make us better thinkers or just better resource consumers?
Right.
It's a vast new architecture for thought that fundamentally alters the cognitive landscape. It's something we are all still figuring out.
Thank you for joining us on the Deep Dive. We hope you feel thoroughly informed.